So let's look at the 4 right-hand rules of electromagnetism. And it can be confusing because if you search for right-hand rules, you'll often just be told one of them. Now let's look at what the 4 of them are and how they relate. So the first rule relates to having a current in a wire. So here we have a wire and there's a current in that wire. What that current does is it generates a magnetic field around the wire. So if you put your thumb in the direction of the current, then curl your fingers around, that will be the direction of the magnetic field that results from having a current in the wire. Okay, so that one's quite straightforward. What about the second rule? So this also relates to having a wire with a current in it. This rule, though, relates to what happens when you have another magnetic field acting on that wire. So that wire will have its own field, just like this one did. If the current's in this direction, its own field will be curled around, just like it is on the left. But let's imagine there's another magnetic field also acting on this wire. And that's when this rule happens. So this rule is with an open palm. You put again your thumb in the direction of the current. Then now you face your open fingers in the direction of the magnetic field, and your palm shows you the direction of the force that's acting on the positive particles or the positive charges in this wire. So here in this case, the current's going up, the magnetic field, let's say it's a magnetic field from this wire over here. So this wire over here, the magnetic field acting on this wire will be into the page because we've got this wire going up, curling around, and now coming down into the page on this second wire. So this second wire, if we use this rule now, use a flat palm, we put our thumb facing up and our fingers flat down into the page, then it shows a force to the left on the positive particles. Now the positive particles in a wire are in the lattice structure. The electrons are the negative particles, they're flowing freely, but the positive particles are trapped in the structure and the force will cause them then to move to the left. So this wire will bend to the left towards this wire. And this is the right-hand rule that tells you about that. Of course, if the current in this wire was in the other direction, then you would have your thumb facing downwards. Still, you would have the magnetic field into the page because that's coming from this wire over here. And then the bending, the force would be towards the right, and this wire would bend out. Of course, this wire also has a field acted on it from this wire here in exactly the same way. So this wire here, if we apply this rule, as we said, the field from this wire is going around this way, so it's acting on this wire will be coming out of the page on this wire. So let's apply this rule here then to find out the force. So the field from this wire is acting on this wire. We put our thumb in the direction of the current, which is up. The field from this wire on this wire is up now, and we have our flat hand and the force is in. So both of these wires, with the way it's shown here, will bend in. So these are these first 2 right-hand rules. What about a third right-hand rule? Well, this relates to coils. And you can see it's a curl rule again, but the directions are flipped. So instead of having the current in the direction of the thumb, now we have the field in the direction of the thumb. So that can be confusing, but I'll show that actually they're equivalent. But let's look at this for a moment. As shown here, the current is going around this way. And if you put your fingers in the direction of the current, which is curling around this way, then your thumb shows the direction of the magnetic field that results in the middle of the coil. And that's a very important thing, which is often overlooked, that this field here is in the middle of the coil. Of course, the field lines go up and then they come out on the outside, and then they meet back up the bottom, these magnetic field lines. So on the outside, it's in the other direction, but this shows the direction of the magnetic field in the center of the coil. Now, how is it that this one and this are the same when they look opposite? Well, let's apply this rule to this scenario. And this rule, we have the thumb in the direction of the current. So this is, in this way, the current is coming, let's look at it specifically for the wire. So on this part of the wire here, the current is going from left to right. So then our curled magnetic field is going this way in here, and you can see, hopefully you can visualize it on the front of this tube here, the field will be going up behind the wire and then down and over in front of the wire. And up behind the wire is in the center of the coil. And as you move your hand around following the direction of the wire, moving your thumb around, you always have the maintained curls of your fingers, so that always on the inside it's facing up and on the outside it's facing down. And that's what this shows here. This is the magnetic field on the inside of the coil. So these two are actually make sense and they match each other up. Of course, when you look at them, you can be confused, but if you understand that this is the current in the wire of a specific wire, then you can see that they do in fact match up. Now, what's common to all of these three rules? One thing is, well, the common thing is that they all have a current source. So in each of these cases, there's a current source supplying current to the wire. And we are learning about either the induced magnetic field or the induced force. So what about the fourth rule? And that applies when there is a magnetic source and the current is the thing that's induced. And so here's the scenario here. You've got a magnet, north magnet and a south magnet. They are going to have magnetic field lines between those two magnets. And here I've drawn a wire in between those two magnets. Now, if we move that wire vertically up, let's say out of the page, vertically up, then you can use this right-hand rule. And the thumb is in the direction of the motion. The fingers, open hand, are in the direction of the magnetic field, and then this palm shows you the direction of the current in that wire if it's in a loop. If it's not in a loop, then there will be a voltage difference between the ends of that wire that would then result in a current if you put the wire in a loop. So here's a wire. Let's look at it for this scenario here. The field lines are from left to right. The motion is vertically up, and so the current is going in this direction here through the wire. Of course, if you reverse the direction of the magnets, or if you reverse the direction of the motion and put the motion going down, then if the motion is going down, then your thumb is facing down, and it's hard to show in the video, but your thumb is facing down and the current would be in the other direction. And this is often shown when we're looking at motors and generators where the electrical wire is in a loop that is rotating vertically and up and down through a loop, rotating in this magnetic field. So this is the fourth right-hand rule. So I think hopefully if you see it this way, you can categorize and can understand clearly. Three of them apply when there's a current source in the wire. One of them applies when there's a magnetic source and the current is induced. So if this video has helped you to understand the topic, please give it a thumbs up. It helps others to find the video. Subscribe to the channel for more videos, and check out the web page in the description below where you'll find a full categorized listing of all the videos on the channel.